Hello, everyone. How are you all doing? Thank you all for attending this, I guess, and on the last day. So my name is Jagan Gudimettla. I am a consultant working for Federal Highways. I manage this rig that you see here. I was getting a little nervous looking at all the slump pictures and videos because in my line of work, anything over 3 inches is rejected. So our primary focus is on concrete pavements. So the theme of my presentation is going to be related to workability of pavements. That's kind of a little different than what the rest of the audience are going to be talking, or the rest of the presenters are going to be talking about. Now, let me first start off by stating the obvious. We talk about durability, but if you really think about it, right, you might design the best mix that's out there that could last 100 years. But if you can't place it, consolidate it, and finish it, it's no good. It's not going to be functioning as long as it should be, or it's designed for. So with that said, the last 10 years have been really interesting on the concrete, in the concrete testing arena, especially related to workability. So one of the things that we do with our Mobile Concrete Technology Center is we acquire new technology that's right out of research. We don't do any research ourselves, but we get technology that's right out of research and try to evaluate the technology and implement the technology in the field. And we work with agencies and contractors and that kind of thing. So with that said, how many of you are familiar or have heard of the Tarantula Curve? A good number of you have. How many of you have heard of the box test? All right, you're in for a treat then. So my presentation slides are going to be very easy on the eyes because I don't have a lot of text. It's just pictures, just like the previous one. These are some disclaimers that our Federal Highway lawyers have asked us to put in. So here is a mobile lab. We go everywhere, and we do a lot of different things to implement new technology. We are a very practical entity. The technologies that we carry are things that you could implement today, not necessarily 5 years or 10 years from now. And we do a lot of different things. One of the major things that we do is we would be invited to a state, and we would be stationed at their construction project, primarily paving projects, and we would be there for a couple of weeks, and we would be sampling concrete left and right. And while we were there, when we take a sample, we do multiple different kinds of tests. So my paper or my presentation today is basically based on data that we've collected from 24 different states over a span of 10 years. This work was actually done during COVID. We are supposed to be mobile, and we were not mobile for a while. So we're looking at what had happened in the previous 10 years. So what we did was we looked at 30 different mainline mixes. These are bread and butter mixes that different agencies do use on their major interstates. And we looked at the Tarantula Curve, which I'm going to talk about in a minute. We looked at the box test, and then we also looked at the finish or consolidation in the field. And our objective is, this Tarantula Curve, which we think is awesome. We were curious to know, with today's mixes, if we were going to use today's mixes and if we were going to apply the Tarantula Curve criteria, how many of them would actually pass? And then obviously the other related question is the Tarantula Curve and the box test and the field observations. Do they actually correlate to each other or not? So for those of you that are not familiar with the Tarantula Curve, this is not just the new kid on the block, but this is the Elon Musk of concrete, gradations. This is something that we've been using for the past 10 years, and we just love it. So historically, on the concrete side of things, we've always looked at aggregates as coarse or fine. We haven't really put emphasis on combined gradation, and that's what this tool does. Basically, what it is we would combine all the gradation, and imagine if you're sieving each of the individual sieve sizes. And once we do that, according to the Tarantula Curve, each of the sieve sizes should meet 3 different criteria. The first one is Well, first of all, the x-axis here represents the sieve sizes. The y-axis represents the percent retained. That's the combined percent retained. So the first criteria is each and every one of those sieve sizes should pass or should meet the criteria that you see there, the bands that you see there. The second criteria is the coarse part of your fine aggregate, which is from number 8 to number 30. If you add it together, it should pass it should be between 20 to 40%. And then similarly, the fine part of the fine aggregate, which is from number 30 to number 200, if you add it together, it should be between 24 to 34%. And something that we've observed is, especially criteria 3 is very, very important when it comes to finishability of concrete. So when we put all these 30 different gradations, what we found out is actually majority of them do meet the Tarantula curve. Only 9 of them did not meet, and even those that did not meet, a lot of times it's just one aggregate that would be, that would be out. So all we really need to do is tweak our blend a little bit, and it would be falling within the Tarantula curve criteria. The second criteria, majority of them actually meet, and it's quite easy, and it's very rare that I've seen that criteria not being met. The third one is basically your fine sand. How fine is your fine aggregate? You want to ensure that you have adequate number of or amount of fines in your mixes. It's not met in a majority of cases, and we've seen time and again that if this is not met, the chance of finishability problems in the field is significant. The Tarantula curve is not the holy grail, but it's a guide. If it fails, the chance of you having issues in the field increases exponentially. But what is the holy grail? Well, the box test is. Now, this is something that's very interesting. It's basically a workability tool that mimics what a paver does. It's a 1 foot by 1 foot by 1 foot box. You dump concrete into the box up to 9.5 inches, take a vibrator with a certain frequency, insert the vibrator into the box, 3 seconds as it goes in, 1, 2, 3, and then 3 seconds as you pull it out. And then immediately remove the formwork, you're going to see a cube like that. And based on the surface of the cube, you can rank it as 1 to 4. 1 being your ideal from a consolidation standpoint. No issues, great finish, and that kind of thing. And 4 is your nightmare. You wouldn't want to use such a mix. On the other end of the spectrum, you also have edge-slump. Paving mix is very unique in the sense that not only should it be flowable enough where you would not have any consolidation issues, but it should be stiff enough to still hold an edge. So that's very unique. So it's like a balancing act. So if you see edge slump, usually top edge slump means you have too much admixture, too much water, you should be able to address in the field. But if you have a bottom edge slump, that means your aggregate gradation, your blend is not adequate. So no matter what you do in the field, you still would have issues. So that's a mixed design issue. So with the Tarantula curve, we were able to go back, we were able to look at all these 30 different mixes. But with the box test, we actually started using the box test in 2015, from 2015 onwards. So we did not had a chance to run the box test on all these 30 mixes. We were able to run them on only 19 mixes. So of those 19 mixes, so what you see there on the x-axis is the project number. That may not mean much to you. It's just a project number. On the y-axis, you have the average box number rating, okay, box test rating. So anything, if you remember, 1 is ideal, right? 1.5 is still good. You can still work with it, no issue. But anything over 1.5, not ideal. So what I'm going to do is I'm going to run through a few examples of bad box tests, good box tests, and then the corresponding Tarantula curve for those mixes, and then some photos in the field. So the first one is this project in on the west coast of the US. I forget what the state it is. Basically, we ran the box test, and the number is significantly high. And if you look at the coarse part of the fine part of the fine aggregate, it did not meet the third criteria. It only had 17% fines. And then it did not meet this criteria a little bit, but that's not a big deal. But when we ran the box test, as you could see, especially on the 3-3 sample, really bad. When we went to the field, this is what we saw. Now imagine this is a $25 million paving job, right? And this is what we've been seeing consistently throughout the pavement. And again, to show you the box test, this is how it looks. So if you look at the reasons why this has happened, well, the mix had a lot of flat and elongated particles, but that's not the primary reason. The primary reason for that is, if you look at the fine aggregates, they actually have 4 aggregates in their mix. 2 of them are fines, but the fines were not fine enough. So all they had to do was replace one of the finer aggregates, or one of the fine aggregates with a finer aggregate. That's all they had to do, and it would have solved the problem. Another project, this is also in the West Coast. Again, not enough fines there. It also had, did not meet the other criteria as well. And this is what we saw. Would you want to have this on your job? Right? So you know what the contractors were doing to address this? They were using water literally after every truck load. And that's basically all, what would that do to your pavement? All the good stuff would come up, right? And what's going to happen to the durability of your pavement now? So all they had to do is just tweak the mix initially, and they would have addressed this problem. Now, on the other end of the spectrum, we have edge-slump issues. Again, another mix where the box rating, the consolidation rating was great, but the Tarantula curve indicated that you're going to have edge slumping. And sure enough, that's exactly what we saw in the field. So my point here is, the Tarantula curve gives us an idea. It's a guide for us to design our gradation so that the likelihood of workability issues happening are reduced. But like I said, it's not the holy grail. It's a guide. But to ensure that you won't actually see that in the field, you have to run the box test during mix design. And if the box test says everything is good, I'm going to go ahead and submit that mix design to the state or the owner, whoever that is. If not, even if all your other properties are good, I would still go back and redo my mix design. So let's look at some good projects. This is from Iowa. Really good Tarantula curve. The box test was good. Again, look at the pictures there. No edge slump and no consolidation issues. And look at the surface. This is from Minnesota. Again, all the 3 criteria were met. Look at the consolidation as well as the edge slump. Now, you would see some bug holes there. Bug holes are okay. That's no big deal. And this is what the finish looks like. Again, you would notice the bug holes on the finish still. This is from Arkansas. If you notice in Arkansas, it did not meet the criteria number 1. It had higher percentage of half-inch. But if you look at the fines, it's actually, the mix was quite fine. It had a lot of fines in it. And they also used some excess cement in this mix as well. So according to the Tarantula curve, it should have some edge slump. But again, with the Tarantula curve, you're only looking at gradation. You're not really looking at how much water is in your mix or how much cement you're putting in your mix. But that's what the box test does for you. So when we ran the box test, it was a perfect box test. And sure enough, that's exactly what you would see in the field. So one of the coolest things with the box test, and I think that's the genius behind the box test, is if you look at the surface, it represents exactly what you see right behind the paver before any finishing occurs. And then my last example here, this is from Kansas. And look at the pictures here. So again, the contractors in your room, the box test is awesome. It's not designed to be an acceptance test, but it's an awesome mix design tool. You can run it in the field, but the biggest bang for the buck is when you're doing a mix design. And in fact, what we have been doing with our mobile lab is, as we go to different states, we are recommending or suggesting that state DOTs include it as a mixed design requirement. They don't even need to tell the contractor that, hey, you will give us a 1 or a 2. All they need to do is tell the contractor to run this, and then no sane contractor in their right mind would provide a mix that would fail the box test. So one of the other things that we also do, we get a chance to do with our mobile lab is not only we demonstrate these things, collect data, but we also get a chance to improve upon existing test methods, give feedback to the researchers. So one of the things that we've done is we are also doing the box test at different intervals of time, just to see how workability changes with time. So here are 2 projects. These were from 2022. Both of them had really good box tests as soon as we ran the box test. However, the one in the top, after 30 minutes, it started to have consolidation issues, right? The one in the bottom did not have any consolidation issues up until like 60 minutes or so. Now, what this actually did in the field is really interesting. Again, everything that you've seen here is real world data. None of this is like lab generated. This is stuff that's actually happening in the real world. So when we went to the field, project A, this is what we saw. And in project A, besides the workability issues, it was also a windy place, so that's also not helping either. So we were having all kinds of issues in the field. The second project, it's in the same geographical area. The finishers, there were just 2 finishers finishing the pavement with really good smoothness numbers in the end. So, all right, so with that said, my last 2 slides, the first thing I would say is, if you have not used the Tarantula Curve, the Tarantula Curve has 2 versions of it. One is for paving applications, the other one is for non-paving, meaning structural applications as well. If you have not, I urge you to to consider it, to use it. You're not going to lose anything by using it. It's just a mathematical spreadsheet. Basically, sometimes we may have really bad aggregates. We may not be able to do much. We may need to get an extra aggregate to help us with workability. But sometimes we are restricted with the aggregates that we have. We have to work with what we have. But the question is, are we really maximizing the aggregates that we actually have? And that's what we could check with the Tarantula Curve. And then meeting the criteria, all the 3 criteria in there is not a big deal. But I would urge you to also make sure that the fine part of the fine aggregates, which is the criteria 3, is always met. Because in my opinion, that's probably the most critical one. And our observations, basically, the Tarantula Curve, the box test, and the field observations, they all correlate to each other in almost all cases. The box test surface finish is excellent. I mean, the correlation is excellent to what you would see in the field. And finally, if you have haul distance issues, or let's say you want to experiment with different admixtures. You want to see how long your mix would stay workable. You can run the box test with all kinds of combinations at different intervals of time. And in the end, it's a great tool for mix design. Again, it's really not something designed for the field. It's primarily for mix design during the mix design process to get a better optimized mix. So with that, happy to take any questions if you have time.